We have today Professor Elena Benvenuti from the University of Ferrara. Thank you to be here. We came just for this seminar, have discussions. So we'll be around this afternoon. If somebody's interested in having discussion, she's available. Yeah, then she's going to discuss, to see the title, so I will not read the title. The only thing I would like to say is that QTT means Quantized
Tensor Train.
So we look forward to discovering what that is.
What is it?
So thank you, Elena.
Okay, thank you again, and I would like to thank Pedro for inviting me here today. It's an honor for me to be here, and I would like to thank you all for being here. This was a joint work with Gianmarco Manzini from National Institute, who is the main specialist in low-rank techniques. I am a civil engineer, just to introduce myself. Gianmarco Manzini is in numerical mathematics. Marco Navi is a postdoc, is a civil engineer also. And Simone Pistolato has both degree in informatics and civil engineering. In this talk, I will first try to contextualize what we proposed, why we proposed it, and the main issues related to this. And we'll just try to give some basics about the method, which consists in the application of the quantized tensor train format combined with a domain partitioning strategy used for finite element simulations of mainly structural examples in linear elasticity, where a lot of degrees of freedom are involved because of the presence of geometric singularities mainly, and that requires a strict match refinement. So just to give you an idea of the main framework we are dealing with. And also I will spend some time about the fact that we have to fundamentally rewrite or rethink all the basic operations of the finite element method, and discuss some examples. So there are many challenges for the computational scientists or computational mechanics specialists striving to increase the efficiency of numerical simulations when considering high-dimensional models, such as in the case of multi-scale models, multi-parameter models, computational homogenization, optimization, quantum chemistry, application of the kinetic theory for complex materials, and also topics which are very multidisciplinary, involving social dynamics, economy, vehicular traffic flow phenomena, many complex living systems. And also we are increasingly facing the challenges posed by the data-driven approaches, data analytics for structural health monitoring, for instance, machine learning-based approaches. They require, of course, intrinsically are closely inherent in dealing with big data, okay, and increasingly in many engineering fields, as we all know. And I would like also to mention that there are cases where I'm more maybe involved, where also the presence of complex geometries, singularities in the solution, geometric singularities, the presence of nonlinear constitutive laws of Softlin type, the existence of localized fields that need to be captured by our formulation, that may increase the degrees of freedom which are involved into the description, such as in the case of the phase field, which is a quite typical case where one needs many degrees of freedom. However, as known, this multidimensional issues, problems are strictly posing many challenges. And the first one is the so-called curse of dimensionality. As the computational cost escalates exponentially with the increasing dimension and with increasing problem size and complexity. And the computational complexity grows like n up to d, where d is the number of degrees of freedom, and d is the number of the spatial dimension. This is quite known, and many remedies have been proposed. Among them, the order reduction methods, where many of the scientists, which are also here, and the work here at CIMNE and LaCàN have provided important contributions, starting from the Ladevez-Leighton method to the proper generalized decomposition. Here I've just reported some of the contributions in this field. Low-rank representations have also achieved a breakthrough in compressing high-dimensional data. And they proved efficient for alleviating the so-called curse of dimensionality. Canonical decomposition is one of the low-rank approaches, but it proved an NP and non-deterministic polynomial half problem that is not always solvable. The Tucker tensor format relies upon the use of tensor-based techniques, and it has also proved effective for reducing the curse of dimensionality. It is, however, most suitable for relatively small dimensions, and that's why there are many researchers which are interested in tensor train format-based approaches, which essentially is the main starting point of the work. Here you see, just in the civil engineering field, where I'm more familiar with, showing the number of the publications in different topics of civil engineering, from the structural health monitoring to earthquake and seismic engineering to pavement monitoring, transportation, urban mobility, and are increasing more and more. So the tensor train mathematical framework was already known before Ojeleget's in 2010 proposal, because it was developed by in the framework of the quantum spin systems. It was known as the metric product states and was conceived for dealing with this kind of problems. Actually, the tensor train format achieves linear scaling in the number of the separated dimensions, and has an almost cubic dependence on the ranks of the tensors that are used for the approximation. The algorithm allows us to compute quasi-optimal approximations of our tensor through a systematic application of single value decomposition, which is recursively applied to arrive to our tensor decomposition. So essentially, the tensor train approximation relies upon the approximation of our tensor depending this A, which depends on B parameters, I1, I2, ID, as the multiplication of G1, G2, and GD, which are the three-dimensional cores of the tensor train decomposition. And actually, the multiplication involves the summation over auxiliary indices, these alpha 0, alpha 1, alpha 1, alpha 2, which concatenate our tensors and are indeed indexes that vary from 1 to the rank of each core of our representation. So the first alpha 0 and the last one, alpha d, are typically equal to 1. And all the other auxiliary indexes are such that concatenate all the cores. I think it is quite intuitive to understand. The TT ranks are the ranks of each core, of each TT core. And essentially, before computing the cores, one has to reshape our tensor so to be able to apply the singular value decomposition algorithm. We will see how. Well, as I said, there is this recursive SVD application. The compression means that we are performing an approximation of our tensor, because when the tensor is not completely exactly low rank, we have to approximate the tensor, and we are able to compute the error bound. And it has been shown that the approximation is quasi-optimal. So it is possible to bound the error, and we can, based on a prescribed relative accuracy, we can compute the truncation threshold for our recursive SVD decomposition, and relate this delta, which is the truncation precision, with the epsilon, which is the error, which we want to achieve. Actually, one of the main drawbacks is that we need for rounding, because every time we perform algebra operations with our tensors, we are increasing the ranks of the tensors. So somehow we have to round, to perform a rounding, to reduce the ranks based on a certain precision epsilon that we have to choose of our rounding. And this part of this rounding comes a lot of time, because each time we perform the algebraic operations between our tensors, we need to perform ex post rounding to reduce the ranks. The addition is performed by merging cores, and also the sum of the ranks are summable. And the scalar product essentially consists in the Kronecker product of the cores. So it is performed by once we know the cores, we can multiply matrices through the Kronecker product. We can also multiply TT matrices with TT vectors, performing at the core level, so all the operations are performed core-wise. This is a picture I made to visualize what's the meaning of considering, for instance, one just entry of our tensor A. Suppose that it depends on 5 indexes, this tensor A, and that we want to select the component, for instance, 3, 2, 4, 1, 3. Okay, so we have 5 cores, because 5 is a dimension, and the first and the last cores are rows and columns, respectively, and the other cores are such that we have to perform the internal summation between indices. The alpha auxiliary indexes are indeed related to the fact that we have to perform the operations between the cores. So the layers which are highlighted in pink here represent exactly the position, the address of our generic component. So you see that the first indexes describes the auxiliary index. The third index in the course is related to the other auxiliary index, and the second index in this case is related to the position of our indices along the depth of these tensors. And so if we think to the MATLAB notation that maybe we are all familiar with, because it's quite simple to perform operations with matrices and vectors, we could see that we could perform this kind of operation with the two dots, right, that we all have used. And this is equivalent to make the internal summation, as we said before, between these auxiliary indexes. Okay, so I think that that should be quite clear. I don't know if you can visualize. I think that it was quite useful to understand. So starting, for instance, from a 3D tensor with these components, we have first to reshape, like the reshape MATLAB command, the tensor, to flatten the tensor like that. And then we apply SVD to this new flattened tensor and compute the SVD. And so we have that this new tensor as a representation in terms of U1, sigma 1, V1 T transpose. And we identify U1 as our G1, as the first code. Then we take B as the product of sigma 1 V1 transpose, and we reshape it, calculate again the singular value decomposition, and then we reshape U2 of this new decomposition. This reshape it and gives the G2, the second core. And then we reshape the product of sigma 2 by V2 transpose in the shape that is required to identify the G3, the third core. So this is how it looks, this decomposition. The G1, G2, and G3 cores are like that. It is called train because, you could also think of a train with the coaches which are concatenated, and the first and the last one are the coaches which frame the limits, the first and the last one of our concatenation. That's why it was called tensor train. What is this? Very strange. I think I lost maybe. Okay.
Looks like it is a blank.
Very strange. Oops. No. Something.
Because this is the thing that you have in your screen, right? So probably you can.
Very strange. Well, I don't know. Strange.
You have the PowerPoint also inside the folder.
Yes. Maybe that one might be saved. will run it again on overleaf and then upload it, because apparently otherwise.
And you generate the command check in your computer that has all the pages.
Yeah, it has all the pages. 50 pages, they are all there. They are all there. So. Okay, because I have all the pages here. And the parent is the same. Wow.
See all the pages here.
Yeah. Well, I don't know. So.
Now it's working, right?
Yeah.
So then you have to share the, no, it's,
Yeah.
no, because
Cannot share.
in the Zoom you have to.
This is not, you have to upload it on the.
No, it's the, just for the ones that are, this one. Yes.
Okay.
Yeah, now you can active again. Time pause. No. I don't know why it's not working the share the screen. No. ¿No puedo compartir? Lo vuelvo a compartir. Sí, ya está. Should work now.
Yeah. It goes here. Okay, sorry.
Okay.
Okay, thank you. So sorry for.
Okay.
So, what is the quantized tensor train approximation? It extends the tensor train approach, but exploiting the concept of quantization of tensor dimensions. Actually, quantization folds into a physical dimension, which is 2 up to d, creating the virtual modes that introduce different scales of our approximation. So essentially, we are creating new dimensions in problems which wouldn't intrinsically come as a multidimensional format. And the transformation is based on creating grids of 2 up to d by 2 up to d in the 2-dimension nodes. So everything has a base 2, and we obtain in this binary form based on the binary indexes related to d, which is the dimension of our grid, the sense that we have 2 up to d elements along each direction. And this process creates n-dimensional vectors made of 2 up to d contributions. And it is an n by d dimensional system. So it is not I don't know. Okay, today is not Friday the 17th hour. The tensor train was invented, was used to deal with multidimensional tensor structures. The quantized tensor train format creates these dimensions. And these dimensions are, in fact, virtual. So the QTT format applies the tensor train decomposition to ND virtual dimensions. And you see here how you organize your dimensions, which, in fact, for each of the parameter, create virtual indices. And so we have levels for the parameter E1, which has n degrees of freedom, the second level for the parameter 2, which has n degrees of freedom, and the parameter ID, the level ID, which comes with the order of our quantization, which can have n degrees of freedom. So it applies to multidimensional problems and to multi-scale models. This is a quite exploited concept. So it is quite new, but it is quite exploited in many applications, multidisciplinary applications. And there are many scientists working on that. The main specialists are 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧, Schwab, and many others. I also put some references along the presentation to give some reference, some bibliographic reference. I don't know if you can see here how the quantized structure of above vectors and below matrices are. So you see that each term is on a basis 2, and all these this is written in the tensor train format with the concatenation. You see that each element has a base 2. This is for vectors, this is for matrices. So the sub-components are matrices 2 by 2, and here are columns of 2 elements. So the key is that you quantize with a base 2 everything. Well, applications of the QTT in the finite element context are quite increasingly appearing on the journals, because the quantized tensor train creates virtual dimensions, and when we are performing finite element simulations, we not necessarily have a lot of dimensions since the beginning, especially in the examples where you have a finer refinement. You have many degrees of freedom, but you are performing 2D or 3D computation. So one could say, okay, you have a low dimensional problem. So why are you using a tensor train format, which was conceived for many dimensions? The fact that is that this quantized format allows you to transform a low-dimensional finite element problem into a high-dimensional problem, and that is quite powerful in diminishing and reducing the storage the time, and all the computational resources that you have to export. It has been essentially in the literature by these applied mathematicians developed for applications on Laplace problems, Poisson problems, Navier-Stokes problems, where the unknowns are scalars. And even if there are applications of the QTT to finite element methodology, so we can find in the literature papers saying that they are presenting QTT finite element applications. None of them are dealing with structural problems, so they don't have the discretization of vector displacement fields, and don't consider the typical problem that is interesting for us, the divergence of the application of a tensor, the consecutive tensor to the strain tensor, and okay, so it is just they are just applications for Poisson and the Laplace equations for scalar problems. And there are also contributions in the isogeometric framework. We essentially started from all this literature, or these huge efforts that was made before us, of course, and especially we considered a paper by Markeva, Ozeledes, and others, Tsibulin and Ozeledes, that they, in the paper QTT isogeometric solver, in fact, they are not using isogeometric, but they are using the finite element method. And they also provided a GitHub, Markeva uploaded on a GitHub repository some Python codes that we have found, and we have started from that. So, and what we did was to develop something which was for linear elasticity, having in mind to apply to structural problems. This implies that one has to think to a total reorganization of all the standard, the basic operations that are commonly used in the finite element method, like mesh reorganization, the node numbering, the degrees of freedom numbering, or the metric stiffness has to be completely restructured. And all the basic algebraic operations need to be restructured. They need to be re-implemented in order to perform our computation. So this is our starting problem, and assuming that we are all familiar with. So it is the divergence of the stress field plus the field of the body forces with, I mean, homogeneous boundary conditions, but it could in principle be applied to any kind of boundary condition. And the weak form is very straightforward, so I'm not going to too much to spend time on this. One interesting point is that in our 2 up to d by 2 up to d grid, because we started from 2D cases, so we think to x and y directions, and you take 2 up to d nodes along x and 2 up to d nodes along the y direction. Since we are constrained to keep to respect this grid requirement, we have to subdivide the domain into subdomains, which are fast subdomains which need to be concatenate each other. So this is our displacement field, which is approximated displacement field, and one has to be careful because you have to exploit the tensor product shape functions. So we started from 4 nodal elements, low order 4 nodal elements, where all the shape functions come from the product of the function, linear function along x by linear function along y. Other, just to make it simple, beyond the mathematics, that is not so important here, but just to give you an idea, all the compatibility, all the stiffness contributions must be thought at the corner level. So think to the parent domain, and the parent domain has the four corners, and what you have to do is to think to all the stiffness contributions for the single corner. So there are no elements, there are just corners in your field, and you make your operations thinking to the corner. And also the stiffness matrix, not an element stiffness matrix. It is a stiffness matrix which comes from the compatibility, of course, and it has to be thought in terms of the corner. So the stiffness matrix C1, C2 means that you have to put into relationship the corner C1 with the corner C2, okay? And you get the reciprocal contributions to the stiffness coming from the contributions of node C2 on node C1 as usual, okay, in our codes. And well, it is very long. Here it's also even cut. So these are all the terms of our. I'm just going a little bit faster because I don't know if you want to interrupt the presentation, but I would like to go faster, okay? Because I'm still still something to tell you. Well, thinking to the QTT format, it was important that every term in the stiffness matrix has to be built in a QTT format, and even the determinant of the Jacobian has to be put in a QTT format. And all the matrices are never stored totally, but they are just computed on the fly. So you never store the stiffness matrix. You're just operating corner by corner, and you never have the complete stiffness matrix. One weak point is the necessity of rounding, as I said before, because every time we perform our QTT operations with our 10-TT algebraic operators, we are increasing the ranks of our representation. And so the rounding is one of the main, maybe weak points of what we are doing, because we have to make a bound to reduce the ranks, and that's why we make it rounding. And rounding comes with approximation in our approach. So the single component of the stiffness matrix in the QTT format has to be rounded. Then essentially you are, I think that it's not so easy to understand everything, but just to give you an idea, you have to think of all our entities as tensor entities that communicate each other through the cores, and each, for instance, each term related to the corner C1, C2 is subdivided into the four contributions associated with the degrees of freedom XX, XY, YX, and YY. So they never are together. They need to be, by means of the connector product, disjointed. That's why we also keep a bound on the ranks, because the ranks here just sum up. And another important ingredient of this formulation, which is, I think, that is strictly required for finite element simulation, is the adoption of the zeta order. The zeta order is very much necessary because it is really a speed up help to reduce the ranks of our course. And the zeta order is a very old concept. Look at the canonical order that we use usually in our finite element simulation. I mean, I'm talking as a civil engineer, so I was just used to implement finite element codes like, okay, no, not a numerical analysis. The canonical order is the most intuitive way to perform the reordering of our degrees of freedom. The zeta order performs like that. You know, it is like something, many zetas that span all our tree. And that's also an additional issue because you have to change the operators, the algebraic operators. So instead of making the Kronecker product of the course, you have to make the zeta Kronecker product. But it can be done. Okay, nothing is possible. And this was just, maybe I can leave you the slides. This was just a computation and application for how to compute the zeta order for the ordering of the degrees of freedom, working with the course of the basic components for our ordering. But that's an issue, okay? So in addition to the new algebraic operators, you have also to think to the zeta version of these algebraic operators, which were amenable to the TT format. So the QTT tensors represent the mathematical objects of the variational formulation in each subdomain directly the zeta order, and they reflect the ordering of the mesh nodes and the cells. The zeta chrome product generates and operates on the course of the compressed QTT representation and acts simultaneously on all the quantities associated with the mesh nodes and cells. Combined with the rounding operation, zeta ordering is quite effective to cut the rest. Once we build, we assemble, make the assembly of our stiffness contributions, considering the QTT domain partitioning, as I said before. We perform the computation of the solution of the system K by U equal to F using the alternating minimal energy solver called AMEN, which was developed by Dolgov and Savostianov in 2014. Now we have used a very basic version. There are more updated versions that can be used. This comes with an error order because it is an approximate way of computing the solution of the system. And this error order epsilon is important because in the meshes that we have investigated for our problems, very simple, they're just representative problems. We have use this AMEN solver, and I will show you the results for variable values of this epsilon, which is the approximation of AMEN. So which examples did we take into consideration? Here you see geometric singularities. These are typical problems in crack propagation. So the L-shaped plate, the T plate, that is the half of a single edge node tensile specimen. Okay, that one is the cantilever, which, as we know, requires many degrees of freedom to be effectively simulated, because otherwise you don't reach the correct level of displacement that you want to obtain. And you see here the red subdomains frame the subdomain. So these red squares denote the subdomains. It is possible to think of adaptive meshes. We mean refined meshes that are not uniformly refined everywhere. But we didn't. We were just trying. This is the first result that we have obtained. So it's possible, but we didn't made it yet. So this is the energy and the L2 error for instance, the double T specimen. Here you see for variable approximation parameter epsilon. So the red line is for the lowest approximation accuracy, which leads to wrong accuracies. So one has to choose a certain approximation for this Element solver, because otherwise we lose accuracy. What you see here is that for approximation accuracies of the order of 10 up to minus 5, 7, 9, the errors are stable, the solutions are accurate, and for 10 up to 8 degrees of freedom, okay, which is a lot, FEniCS couldn't perform the computation. Actually, we have exploited not super computers, so we just had in mind to make something that which was also maybe implemented, possibly implemented into simple laptops, smartphones, just having in mind that cutting the storage requirements could be something that could help, to reduce the computational storage, to reduce the computational requirements. So here there is no particular care for speeding up computations in FEniCS. We just took a quite performant, a quite good PC, but didn't push too much on the performance of the CPU. But here you see that FEniCS cannot reach the same values of degrees of freedom. The slope is the correct one. We have checked it based on the references. And this is the case of the single edge notch specimen. Again, we have to choose a sufficiently accurate alien approximation. One of the main points, weak points, is that beyond a certain level of degrees of freedom, you cannot go with accuracy. You do not gain much accuracy, because you are conflicting with the accuracy of the algorithm that you are using. So you cannot go beyond at least the minimal accuracy of your Element solver. Okay, so you can go with as many degrees of freedom as you want, but beyond a certain level of degrees of freedom, you have to think how to improve the performance of the Element solver, and that's possible also. But this is interesting because you see on the left, you see the memory in terms of the megabytes which are involved in our solution, and you see that FEniCS goes exponentially with the logarithm of the degrees of freedom. Okay, so it's a huge of memory which is involved in FEniCS, while with the QTT, look here. So this is quite impressive. It's completely cut off of the storage of the memory. On the right, you see the ranks. Well, in both cases, for the time and the ranks, you see that there is a domain of degrees of freedom beyond which it is not so convenient to make that QTT. Okay, but beyond a certain level of degrees of freedom, it is convenient because it cuts really much the storage. And for the ranks also. So you see that the ranks of the matrices is tending to asymptotically tending to a fixed value, which is not so high compared to the number of degrees of freedom that we are dealing with. This is again the same for the cantilever. So the same principle. FEniCS grows exponentially, cannot go beyond, and with over certain degrees of freedom. Here you see on the left the time which is required by our computation, and on the right measure of the ranks, which is an equivalent rank, which is a global indication of the ranks involved in your QTT decomposition. So the time versus the logarithm of the degrees of freedom shows that FEniCS cannot go beyond the second level of degrees of freedom because it explodes little, cannot go beyond. And this is the time. So it is almost quite sublinear. I mean, in the logarithmic, in terms of the logarithm in the basis 10 of the degrees of freedom. On the right, you see that this equivalent rank is related to epsilon, the accuracy of Eyman. So the more accurate Eyman, the larger the ranks which are involved, which is expected. And also that increasing D, so taking, for instance, 2 up to 5 by 2 up to 5 nodes gives ranks which are smaller than taking 2 up to 11 nodes by 2 up to 11 nodes as expected. But again, the equivalent ranks are quite small. This is an investigation that we made based on 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧 paper of 2018 that showed that there is an exponential convergence in terms of the errors, provided that you plot your error that way. It is a bit complicated, but it is exponential with exponential k equal with exponent k equal to 5 in terms of the logarithm of the representative number of the parameters and d, and in terms of the logarithm in base 2 of the inverse of the error. Here you see that also, so in the first picture, there is the energy semi-norm error, and the line, the continuous line, is the reference exponential convergence of equations, which is an exponent, but an exponential equation, but in the logarithmic, by logarithmic plot, it is a line for increasing number of d, the dimension. Here you see the energy semi-norm, and the reference line is, as I said, the logarithm in basis 2 up to k of ed, which goes like with the k equal to 5. And then here you see the maximum rank of the QTT approximation. And again, the reference line, it was the continuous line, it is an exponential, and these are the parameters which can be obtained. So essentially, what we get is that we confirm the results by 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧 that QTT, even with a linear elasticity, the divergence operator for the vector case achieves the expected slope of convergence, the slope of convergence, and exhibits the desired efficiency compared to traditional FEM. Displays the maximum rank displays a sublinear convergence in terms of the degrees d, and this is also an indication of the CPU cost and memory savings of our formulation. So here we have extended the design of the QTT finite element method proposed initially by Markeva to vector problems. And combining with the zeta ordering and the subdomain concatenation, the approach achieves significant gain in terms of storage and time, and a remarkable rank reduction compared to traditional finite element. Well, the trade-off relies upon the need for introducing a change of the implementation paradigm, because we have to restructure the mesh discretization, the ordering, the stiffness, everything has to be redesigned from the beginning. And the hope could be that since these results are quite promising, one could think of performing this computation on laptops, smartphones, and to possibly extend this technique to more complicated problems, also multi-scale problems, multi-dimensional since the beginning problems. Another possible combination of the QTT is the quantum computing, which is reminiscent. I mean, the word quantum is the same, but it is very much a strategic issue for the European community and also worldwide. And it is known that, as also the papers by Michael Ortiz and the co-workers, recent papers, the quantum computing is quite promising in terms of possible reduction of the computational burden of our computations. And it's true that in common there is this quantization of the basis, but for the quantum computing, then you have that the quantities which are involved are not deterministic, while in our case they are. And beyond the similarity between the structure of the data, which is quite evident, there are also applications in the literature of researchers which are working to bridge the QTT with the quantum computing. So it seems that there is room, okay, for this line of research. And there are also companies like Terra Quantum, which is a Swiss company. They're publishing also papers on QTT and quantum computing. They are working on industry-oriented applications, so combine all these two technologies. So it was just to give you a hint, basically, somebody could also wonder whether there was a relationship between these two, similar, at least semantically similar topics, okay? Of course, I would like to thank you very much for being here, and it was a pleasure for me. I hope you're not too much bored. So please, if you have questions, I'm here. It was nice to present it to you. Thank you.
Thank you, Elena.
Thank you, Elena. So I have confessed that I missed most of the technical details, but you showed for some of the L-shaped specimen, you showed very impressive results regarding the savings in memory storage. So is your plan extending all this to nonlinear problems?
Yeah.
You mentioned phase field or damage.
Yeah, that was. I'm coming from that, so everybody has. I'm open to other applications, but I have this background in computational mechanics, which I may be interested in doing this, but I'm also open to other applications. I think that there is room for many applications, because you could say, okay, you have a low order finite elements, okay, so why should you complicate things too much, okay? But we are in fact obtaining striking results. So
Because when you say FEniCS in your results, FEniCS is just a representative standard finite element form, right?
well, I thought so. It is quite optimized, I guess.
Okay.
But
one more question is a curiosity because I know that you didn't apply this steps to parametric round.
yeah, that's also
But still, what this quantized concept, which correctly is at the end of the day, is just putting together sets of indices. So
yeah,
writing quantums or
they are
packages of
yes,
indices putting together. In the context of parametric problems,
yeah,
I see a parallel with that and putting together sets of parameters.
yes,
We have scalar parameters, and we have done that with PGD just
yes,
to
yes,
discretize not one parameter but in 2 or 3D packages of
many,
2 or
many.
3 parameters.
Yeah.
And then it's easier to
But you,
separate in the PGD framework. And I don't know if there is a parallel in the two ideas, the idea of collecting indices
the course, they're looking at the course if they have some
exactly.
relationship. But it's true that you have to have a tensor structure. Without the tensor structure, cannot make it.
Yeah, but we will have it.
Yeah.
Parameters.
In terms of the parameters.
Of Cartesian
Okay.
grids of
I think that would be also an application that I would be very much interested. Also for civil engineering applications, you know, monitoring, health monitoring, and I think it is a very promising research line.
Okay. Is there any other comments or questions? Or if it's not the case, let's thank Elena again.
Thank you.